All right, good afternoon, everyone. Hope you had a good weekend. Let's get started. Does anybody have any questions on the midterm this Friday? Okay, great. No questions. So let's finish up the classification unit that we were working on. We're almost done. So last time we were talking about the way that you measure performance for binary classification. And we wrote out this confusion matrix, which shows the 4 different possibilities of what can happen with the true label and the predicted label. And we noticed that there's 2 different ways to make an error. And in some applications, it's safe to treat those as equally bad. But in other applications, like we talked about cancer diagnosis, one of those might be a lot worse than the other, and so you don't want to treat them the same. And so accuracy is a metric where essentially you are treating those 2 errors the same in terms of importance. That's sort of the default metric, but like we said, that might not be what you want to do. So we have some other metrics like precision or recall. Both of those, so for example, in terms of interpretations, given a positive test, how often is the patient actually sick? Or given a sick patient, how often is the test correct? So on. We have interpretations for them. These would actually give you a pair of metrics, and if you had a pair, it wouldn't be really clear like what's better. If one is, precision is better and recall is worse, do you say that the method is better? So there is a way you can average them in terms of F1 score to reduce them to one specific number. And then we have similar things we can do, similar concepts in medicine like sensitivity and specificity. Okay, so this is one thing we talked about. These precision, recall, F1 score, accuracy are very easy to measure in sklearn. They're part of those default list of scores you can use. And then we discussed another sort of freedom you have. So when you train logistic regression, you are not training it to maximize accuracy or precision or recall or anything. You're just training it to minimize logistic loss. Okay, so it does not really care what you're interested in. But when you finish training it, as we know, you can compute these scores, you can compute these soft decisions, but eventually you may need to compute a hard decision. And at that point, that's where these metrics come in. That's where you're actually making errors and so on. So at that point, you do have the flexibility to use a different threshold than 0.5 on the confidence. So if you say my confidence is a soft decision that's between 0 and 1, if you threshold that at 0.5, that would be the right thing to do if you want to maximize accuracy. However, if you want to somehow balance precision and recall in a slightly different way, you can use a different threshold than 0.5. And when you do that, you can see if the threshold increases, precision goes up, which is good, recall goes down, which is bad. So here, it's not really clear maybe until you get into the details of the application exactly where you want to be in terms of the precision recall trade-off. So that's something that you need a lot more information to decide, but there's a way, once you know what you want to do, there's a way to deal with it just by changing that threshold. And there's something very similar here for sensitivity versus specificity. And then we saw one more very similar trade-off. This is between TPR versus FPR, true positive rate, false positive rate. So when you look at this, as the threshold increases, the true positive rate comes down, which is it's getting worse. But the false positive rate is also coming down, which means it's getting better. So as you move to the right, one gets worse, the other gets better. It's not exactly clear what you want to do. Maybe you need to know more about your application to decide that. But once again, you can choose T, the threshold, to navigate that trade-off. And this is a particularly important pair because people often plot these two quantities versus each other here in what's called the receiver operating characteristic, or ROC. And so here is just another visualization of this plot that we saw below, where you're plotting TPR versus FPR as you vary that threshold, and you can see you go to all those different trade-off points. Ideally, you would like to be here. It's not really clear which of these is closest to here in the right sense, but you can see you have several choices that you could make. So if you don't know exactly where you want to be on this trade-off curve, then what you can do as a way of measuring the overall performance is you just take the area under the curve, which is obviously something that increases as the curve gets closer and closer to that top left quadrant. And so this is a very popular way of measuring performance, different from accuracy, that's trying to get a different balance, yet is still threshold independent. It's probably the most popular one that I've seen. So, okay, and then we talked about how to do that in sklearn. Okay, so any questions on any of those concepts? Okay, so that's all for binary classification. Now let's think about what happens in multi-class classification. So in this case, our confusion matrix is a lot bigger. So if we have capital K classes, we have a K by K confusion matrix. So the terms along the diagonal here are measuring correct decisions. So like when the truth is 1 and you predict 1 and so on. All the counts off the diagonal are measuring errors, but there's many, many ways to make errors here. If you're given a confusion matrix like this that has just raw numbers in it, it's hard to interpret it. So what's more common is to normalize the rows so that they sum to 1. So for example, if we make all these values sum to 1, then we have a valid probability mass function, given that y is 1. Given that truth is 1, we see the PMF of the decisions. So that's a typical thing. So in that case, for example, the kth entry in the table becomes the probability the y hat is L given that the truth is K. And we also, in that normalized case, the diagonal terms give us our per class accuracies. So the accuracy if the truth is K for different K. And so this is a very common thing to do, is to normalize that confusion matrix. Okay, so as you can see now, there's going to be capital K different per class accuracies along the diagonals. And if you're interested to know what is the relationship between those per class accuracies and the overall accuracy, it's given by this equation here. So if you're familiar with conditional probabilities, you might immediately see that this must be the case, because when you multiply these two things here, you have probability y hat given y times probability y. Does anybody know what this is? In terms of probability, what is this? The joint probability, exactly. So together, this is the joint probability that y hat is K, comma, or and y is K. And then second step is if you take this joint probability and you sum over one of them, then by the law of total probability, that just removes that dependence in your okay, so yeah. So essentially what it does, it's essentially going to average over all those different cases. So this is how the overall accuracy relates to the per class accuracies, and it will be important when we talk about what happens when these guys here are not well balanced. We'll talk about that on the next slide. But so here's overall accuracy. This is probably the most common metric people use in this multi-class setting, although as we know, it may not be what you want to use if you care about some of these accuracies more than others. Now you might wonder, what about all these other metrics here like precision, recall, what do you do with those in the multi-class case? And so there's actually different things you can imagine doing here. But after looking into it, it seems like the most popular, most robust choice is if you want to do a multi-class precision, you use these what's called a micro-averaging of the K versus rest metrics. So let me first describe what is this K versus rest metric. So let me make a little table here. So this is going to be y equals k. Let's say the top y is not equal to k. And then we have y hat equal k, y hat not equal to k. So for example, if I'm focusing on k equals 1, then this would be what's there. This block would sum over all of these. This block would sum over all of these. And this block would sum over all of those. Okay, so these are the one versus, or K versus rest metrics. So we can give these names. We can call this the true probability sub K. Let's see, what do we have? Then we have, it's basically the same as this table. False probability K, false negative K, and true negative K. Okay. So depending on which value of K you're holding out here, all these numbers will change. Okay. But for any given K, you can compute those numbers. And then for precision, you use the precision formula that we saw on the previous page, except that you do a separate average over K in both the numerator and denominator. And it's a similar thing for recall. And if you want to compute the true probability and false probability rates, then you can again use those K versus rest metrics in this way. So these are nice ways to generalize these different definitions for multi-class classification. Okay. Any questions? Let me just put a little arrow here. Are there any questions on anything here? Performance for multi-class? Okay, so just have one more topic to talk about then, which is imbalanced class labels. So what we mean by this is a case where some classes have many fewer samples than others. Or probabilistically, you would say, in the multi-class case, the probability that you get, probability of y being in a particular class K is much less than 1 over the total number of classes K for 1 or more K. So let's just talk about the simplest binary case. Let's say you're doing something like COVID testing. And let's say your population you're testing is 99% healthy, 1% sick. So think about that case. If somebody told you that they had a 99% accurate test, should you be impressed? What's an easy way to get a 99% accurate test when your population is 99% healthy and 1% sick? Say everyone is healthy, exactly. So you have a trivial test that always predicts healthy, and it's true 99% of the time. Obviously, it's trivial, it's useless. So you don't want to get fooled by high accuracies, especially in the case that you have imbalanced labels. So this is a serious problem in practice because it's actually something that shows up a lot. And so, there's a few different things we can do about it. So where this problem is coming from, this problem I just described in the binary case, you can kind of think about it according to this equation that we saw on the previous page. So this is the case where I said, one of these is 0.99, the other is 0.01. And if I want to get 99% here, then what I could do is I can make a trivial classifier that sets this probability y equals k, 100% chance it does this for my majority class, 0% for my minority class. And the reason why this is failing is that this guy is assigning all the weight to the majority class. So if you want, one simple way to try to get around this is what's known as balanced accuracy. And in balanced accuracy, you just throw away this term. You throw away that weighting term. So now you're just measuring, the sum of those kind of more raw conditional probabilities. And this is just one approach. It's not the only approach, but it is one thing that you can look at. Interestingly, another approach that some of you might be thinking of is, well, let's say I take my data set, that same data set where I have 1% unhealthy, and maybe what I could do is I could just copy and repeat that unhealthy, all the unhealthy samples, I just copy and repeat them 99 times. And so now I do have redundancy in my data set, but at least it's balanced. I have equal number of healthy and sick. And if you do that, and that's not a terrible idea actually to do that, you can do that, and what you would find is if you evaluate accuracy in that case, you would get the same thing as this. So it's just sort of a more direct way of doing that where you don't actually have to do any copy and replace. You can just measure that metric directly. Okay, so this is one thing you can do that might give you a more reasonable metric for this imbalanced case. Another thing you can do is you can look at metrics like the area under the curve of, this is the precision recall curve. So instead of the receiver operating characteristics, which is TPR versus FPR, this is precision versus recall, but it has a similar shape. And because we don't know exactly the threshold we want to use for precision and recall, what we can do is we can just look at the area under the curve, threshold independent, not have to make that choice. So these are probably some of the most popular ways to measure performance in this imbalanced setting. Yes?
Shouldn't there be 1 over k in balanced equation?
Yes. Well, actually, yes, there should. Yeah, thank you. There should be 1 over k. Otherwise, the number we're going to get is going to be too big. Sorry about that. So there should be a 1 over k here. Okay. All right. Okay. So that's one piece of the puzzle. The other thing that can happen is, as we said, when you train logistic regression, it doesn't really care about whether you're interested in accuracy or precision recall. It just minimizes logistic loss, which is nice because you don't actually need to make that choice for training. However, in this highly imbalanced setting, if you train and 99% of your samples are in one class and 1% is in this other class, you would find that when you minimize the logistic loss, you're looking at a sum of loss over your training samples, that this would be, again, highly imbalanced because most of your loss is coming from the one class versus the other. And that would cause even this logistic training to be probably suboptimal. It's going to focus too much on the typical case that happens, which is healthy patients. So scikit-learn gives you a pretty convenient way to deal with this. All their classifiers have an option called class weight. And if you set that option to balanced, then what it will do is, okay, I haven't read up on the documentation since last term, but I think what it does is it weights this loss so that whenever you have a sample from the minority class, I think it basically increases the value it uses in the sum. But the details are here if you want to read about it. And this is a nice way to make the training more robust to this class imbalance. Okay. Any questions there? Okay, and there's one more thing to think about, which is k-fold cross-validation. So again, let's say you're doing k-fold cross-validation, and let's say you're doing k equals 10-fold cross-validation, and let's just say, for simplicity, that your data set has 90% majority samples, 10% minority samples. So in this case, what ideally would happen is every fold would have 10%. Well, okay, all the folds in cross-validation would have that 10-90 split. Right. But that may not be happening in reality because the folds are randomly generated. So you could have some folds with a lot more minority samples, maybe other folds with no minority samples. And so when you start to do k-fold, the results are going to be a bit off. They're going to be more random than you'd like because there's this inconsistency due to the particular shuffle. So there's an approach to k-fold called stratified k-fold, which makes sure that all the folds have the same class balance as the overall data set does. It just forces that when it generates the indices for the splits. So that's another thing. So you have this stratified k-fold, balanced class weights when you do your training, and with these two things, you can make your classifier more robust to this presence of imbalanced class labels. Okay, so those are the main tricks people use. There are other things people have proposed, and you can find some vigorous debates online about what's the right thing to do, but I think this is sort of the most common practice here. All right, are there any questions on anything here? Okay, if not, I think that's all we have for this unit for classification. Though that's not going to be the last thing we say about classification, because we'll actually spend the whole few next units on it, but just different aspects of it. This is sort of the version 1, simplest version, logistic regression, then we'll get into some other versions as we go. All right, so are there any questions on anything classification related before we move on? Great, okay, so let's move on to unit 6 then. So this is going to be a unit on optimization. What we learn here is going to be super important, especially once we get to neural networks. But basically, our motivating example, our main demo here, is to build an optimizer for logistic regression. So in the last unit, we said, okay, logistic regression is something that we can't derive the optimal solution analytically, but we can use sklearn. sklearn knows how to do it. So now we're going to try to understand what is actually going on under the hood in sklearn. Can we build our own optimizers for problems like this and other problems? So let's just first start. Okay, so does anybody remember what was the binary logistic optimization that we derived? So, I imagine you guys have probably not memorized this, at least not yet. So I'll write this down. So we're going to do an optimization or minimization over W, and our cost function, which we call the binary cross entropy loss, looks like this. We have a log of 1 plus e to the power zi, and then we have a minus yi zi, and the dependence on w comes through the zi. So zi, we're going to write it like this. We're going to make a row vector 1, and then to the right x transpose or xi transpose, and then we're going to have the w vector here. So just to kind of point out, change the notation a tiny bit. Instead of calling the intercept term b, I'm going to call the intercept term w sub 0, which is very similar to what we did back in unit 2. We had beta sub 0 as the intercept. Now all the weights are w. And what's nice about this is we can just refer to the weights, all the weights together in this weight vector w, and not have to do b and w together. Okay, so this is what we derived in the last unit. This is the specific case where the targets are either 0 or 1. So that's how this manifests here. And yeah, so we know how to do this in sklearn. The question is, can we do this ourselves? Okay. All right, so to do this, we're going to have to go back and talk about gradients. We've talked about them before, but we're going to talk about them in a little bit more generality now. And the first thing is to reflect a little bit on, or review, really, what gradients are. So the reason we focus so much on gradients is that we are interested in finding the minimizers of cost functions. So we'll call our cost functions J because that's what's very common in the optimization literature. And so J could be, or sorry, it shouldn't be J of X, it should be J of W. An example of J would be this whole thing here. This could be, this whole thing could be J. But, we're not going to focus specifically on that. It could be anything else we want to minimize. So this is what we're interested in doing. And we said the gradient is very useful. So the gradient, we're going to denote it with this upside down triangle, also known as nabla J. So the one really nice thing that happens with the gradient is at the location of that minimizer, the gradient goes to 0. So if this is a vector gradient, then we have here the 0 vector. We also know that the gradient gives us the direction of maximum increase of the surface. So let's look at this picture. So in this picture, the little arrows are showing us the gradients. The direction the arrow is pointing in shows us the direction of the gradient, and then the length of the arrow shows us the norm. And so what this is showing us is that if you're right here on the cost function and you're looking directly uphill, you'd be looking in this direction. And as you move around over here, if you're right here in the cost function and you're looking downhill, you're still looking uphill, you're looking in that direction, and so on. So that tells us that, is this a peak or a depression here? Peak, right? Because all the gradients are pointing up to it. And then this over here, all the gradients are pointing away, is a depression. Everything's going out. So when we have some sort of complicated cost function J like this, and we're looking for the location of the minimum, so essentially like these numbers, if we can somehow search around and find the location where the gradient is 0, then perhaps that might be the minimum. But you might notice here there's another situation. This over here is another place where the gradient goes to 0. So that, we don't want to find that. We'll talk about that in a moment. But there's actually different places where you can find the gradient going to 0. But the minimum is one of them, and that's the thing we're interested in. Okay, so we have the gradient tells us the direction, but it also tells us the slope, essentially how steep is it going uphill. And we'll get into why that is. And last comment is that this gradient might not always exist. It does not exist if this thing is not differentiable. At a point of non-differentiability, there is no gradient. But we're going to assume this is not happening. Throughout most of this unit, we're just going to say we have a cost function that is differentiable, so let's not worry about this thing existing or not. We just assume it exists. Okay. And then another thing we're going to do is we're going to use gradients to linearly approximate functions, but we'll do that in just a moment. Okay, so how do we define the gradient? Well, it really depends on the shape of the quantity we're minimizing. So what we've focused on so far is when we're trying to minimize with respect to a vector. So in other words, this W is a vector. So in this case, we said that the gradient had this form. It's the partial derivative of the cost with respect to the first element in W, and then the second, and so on, all the way, the partial derivative with respect to, of the cost with respect to the last element, which we've been calling D. Actually, sorry, the first one should be a 0 because our indexing is starting at 0 now. Okay, so this is what we saw previously. This is a vector valued situation. Okay, so, okay, any questions? So let me ask you this. What about this J? Does J have to be a scalar? What happens if J is not a scalar? Does anybody know what this is called? No. Jacobian, exactly. So when J is a vector, which will never happen for us, by the way, it does show up in machine learning quite a bit, but it's not going to be in our course. It's a little bit more of an advanced thing. In that case, you would essentially, for every element in J, you would get a separate column, okay? But I want to point out that in our course, you can safely assume that the thing we're optimizing is going to be a scalar. Okay, so we're always dealing with scalar valued things. We're just trying to minimize one particular thing. Yes?
It's a Jacobian if J is scalar valued, or
No,
it's a
vector
Jacobian if
valued.
it's matrix valued?
If J is a vector, then you would have to take this derivative with respect to each term in the vector, right?
Right.
And then this thing would become a matrix. But I'm saying we're not dealing with that. We're focusing on scalar valued costs. We're just trying to minimize one single thing. And that is going to give us this gradient vector. Okay. All right, so what do you think happens if we are optimizing over a matrix? And we have seen this, right? We've seen in linear regression in lab 4 when we had multiple targets, we actually had to optimize over a whole weight matrix. We saw also in multinomial logistic regression, or actually any kind of classification problem, linear classification, where you have targets from 1 through k, where k is greater than 2. Then you have like a whole bunch of different predictor W's. You have a matrix you have to optimize. So in all these cases, we do have this situation. So what do you think happens to the gradient in this case?
Become a matrix of partial derivative of J with respect to like W00 and so on.
Exactly. You just get an entire matrix. So you get, so the first one to be like D00, if we're counting from zeros, DJ, and now we want to make sure that we index in the same way we would index W. So usually the first element is going down the rows, second across the columns. So it'd be, D W01, and so on. DJ, D, here you'd have 1, 0. Here DW11, and so on. Okay, so to make this clear, if all you remember is the following, it's easy. The gradient always has the same dimensions or the same shape as the input. So if you start with a vector W, the gradient has that. If you start with a matrix W, the gradient has exactly the same matrix dimensions. If you start with a tensor would be like a matrix but with one more dimension, like a 3-dimensional data cube. Then your gradient is also a tensor with those same 3 dimensions. So whatever the size of W is, that's the size of your gradient. Okay, so now we have the definition. Do you have any questions on the definition? Okay. So let's just do some simple examples. So let's say that this is our cost. And the cost is written in terms of these numbers W1 and W2, which are the first and second elements of this vector. So what do we have for the first partial derivative? I've been bad about calling attendance, so let's maybe get back to it. Is Spond Meta here? Spond? No? Okay, what about, there's a 6-part name, Mior Daniel Hakim. Is this sounding familiar? No? Okay, what about Madhav Muthyala? No? Okay, what about Ryan Flanagan?
For the first derivative, that would be just 2W1 plus 2W2 cubed.
Yes, exactly. 2W1 plus 2W2 cubed. Okay. And then what about the next one? Let's see, Zifei Huang? Yes. Oh, Zifei? Yeah. Okay. Zifei? There are 3 Huangs here, so I apologize. Okay, so Zifei, yeah.
6W1 W2 squared.
Yes. Okay. Great. So, yeah, hopefully this is all very straightforward stuff you learned many years ago. So those are the different components, and now we basically just stack them into our gradient, right? So because dj dw1 is the first part of the gradient, so that's going to be 2w1 plus 2w2 cubed, and we have 6 on the bottom, 6w1 times w2 squared. Okay, so so here is how you would write the code. And so the first thing I want to point out is that almost always when you write code to do gradients, you also compute the cost j itself. You compute the cost as well as the gradient. And this is because typically, as we'll see, we'll talk about why we're doing this. We essentially want to do something like walk downhill to the bottom. So you're going to take a step in the gradient direction, then another step, and so on. And as you do that, you want to keep track of what are the values of the cost. Is the cost actually decreasing? Does it seem like I'm coming down and bottoming out? And so you compute the gradient and the cost together. So in this little piece of code here, this is just defining a little function in Python. You can see we are computing this here, the cost. We're computing both of these scalars, and then we're packing them into a NumPy ND array. And that is what we want to return because we want to do our linear algebra, all our processing in NumPy. So we want to pack this into a NumPy array. And then here's an example of how you use this. We're just creating an example of W that happens to be the numbers 2 and 4. Then we're sticking that vector into our function, and out comes the cost and the gradient, and then we're printing them, and these are the values that we're getting. Okay. All right, any questions on this one? Okay, let's do a slightly harder one then. So in this case, we have this model. So if you look at it, it's maybe somewhat recognizable. We didn't look at this exactly, but you can imagine, looks a lot similar to things we've done. So here we have something like RSS, but over here we have a particular kind of y hat I that depends on some scalar value xi, but this is actually like an exponential model. So you have a gain that's inside the exponential and then one outside, a and b. And so you might wonder, like, how do I set these two parameters, a and b, so that I can take my scalar feature xi and make a prediction from it that best matches my training targets yi. So we know how to do this. We can say, well, let's define this cost and then try to minimize it. So we said First step to minimizing it is deriving the partial derivatives. So what do we have here for the first one? And let's see, we have, is there anyone else I haven't? Okay, is Joseph Wintering here?
Yeah, weird.
Okay. All right, so what do you think is the first DJDA?
Negative e to the negative bxi times that same quantity yi minus a e to the negative bxi.
Okay, I think you're missing that. That's all part of it, but you're missing something important.
The summation.
The summation, exactly. So we have to have our summation over I. I mean, one way to see that it's missing is if this is not there, you can see that this has a dependence on I. It's like you have to know which training sample you're working with, and we're working with all of them. So that's why we need to have that sum there. Okay, so yeah, hopefully you saw that. That's chain rule. We've done a lot of chain rule. Basically you take this, you exploit the linearity of differentiation in the sum. You can sort of move that partial derivative inside the sum, work on this, but then you have to remember to include that sum there. Okay, the next one is a little bit more complicated. Let's see, is John Lemus here? Yeah. So what do you think about the next one?
Summation of n
Oops. Okay.
and then yi minus b.
Okay, so we will have this whole thing, right? So when we do chain rule, so we take this, kind of move it inside, and then we're evaluating the partial derivative of this. So we're going to get 2, which is going to cancel this, times this whole thing. So let's write that out. That's going to be this. And now we're going to have the partial derivative of this with respect to b. So what do you think that's going to be? So we have to do another chain rule now. so this is not going to matter, right? So let's forget about that. So we have to exploit the fact that d dB of e, what is this? So the thing about exponential is that when you differentiate it, it doesn't change. So you end up getting this thing again, and then you have to take the derivative of this with respect to b, which is going to be minus xi. Okay, so that is what goes in, and oh yeah, and then we also have this a term as well. Okay, so after all of that, we have a xi e to the minus b xi. And sorry if I don't want to make that look like a minus sign there. It says a xi. Okay, so yeah, so the chain rule is, we're going to be using a lot of that, so good to get some practice there. But basically, once you have these guys computed, then you just pack those numbers into this vector. That becomes your gradient, and that's it. When we code this, though, we want to be careful. We don't want to waste computations if we don't need to. So when you look at these equations, you notice that there's some repetitions. So for example, this term e minus bxi, that shows up 5 different times. And when you compute things, evaluating exponentials is a lot more expensive than multiplies or adds. Same thing with sinusoids and so on. So you want to minimize, especially those operations. Don't do them more than is necessary. And yes, if you have just a few samples, then it doesn't really matter how you do this because it's going to be lightning fast. But when you start dealing with like millions of samples, things slow down considerably, and it's really important to be efficient. So to avoid the unnecessary duplication here, okay, so let's just look at the beginning. So we have a function here that's going to take in a vector of all these y's. It's going to take in a vector of our training samples xi, and it's going to take in a vector, in this case, of just two numbers. And the first thing we'll do is we'll unpack the parameters a and b. And now let's compute this term once, and let's just give it the name c. So now we have that c computed. Next thing we can do is we can compute this term, which shows up twice. We'll call it the y error. And so this is going to be y minus a times c. Let's think about what's happening there. So this is a scalar, right? But we don't want to do for loops. You never want to do a for loop if you don't have to. So you don't want to implement the sum in a for loop. You want to use vector operations. So we can imagine that this is a whole vector of things here. We can exponentiate our vector of xi's. That's actually what's happening here. So Python or NumPy is smart enough to know that if you have a scalar b and a vector x, that this multiplies that scalar times all the elements in the vector. It's also smart enough to know that for the resulting vector, you want to exponentiate every term in that. And so now this is going to be actually a vector of all these different terms for the different i's. So in computing the y error, now you have a scalar times a vector. It knows how to do that. Now you have a y error vector. And finally, we're computing this. So we have y error. Now we're going to take it to the second power, square it. That's what this is doing here. And then we're going to sum, multiply by 0.5, and finally we're going to get a scalar cost j. So all this kind of stuff about how NumPy, what it does when we work with vectors and so on, and how it like automatically extends things. We'll start talking about this a lot more in this unit because we're going to have to be a lot more clever when we program things. Okay, so any questions on how we computed j? Everybody good? All right, so let's now look at some of these other terms. So we have this computed as y error. We have this computed as c. There's a negative sign here. And so now this is actually we call pointwise multiply. Okay, so in MATLAB, the syntax would be very different because MATLAB, it would be trying to do a matrix multiply here, but in NumPy, a single asterisk is just it's like a dot star in MATLAB. It's just a element-wise multiply. First y error times first c, then second y error times second c, and all that, all the way down. So you have a whole vector, summing across that vector, negating it, and we finally have this quantity computed. Okay. Similar for this next term here, a little more complicated. We have our c term, have our x term, so that's going to be element-wise multiply. A is a scalar, and then y error is another element-wise multiply. So that's how we get this. Now we have these two scalars. We can pack them into a NumPy array, 2x1 array, and that's what we return. We return that gradient array and j. Okay, so and then just as an example, we generate some random data, we set some arbitrary parameters, evaluate the cost and the gradient, print them out, and this is what we happen to get. Okay, any questions on anything here? Okay. Okay, so so just a little bit on computing gradients. So now let's turn our attention to this idea of approximation. So this is another useful thing we can do with gradients, is essentially we can take a complicated nonlinear function and we can approximate it as linear in a certain neighborhood, and this greatly simplifies our understanding of it And in some cases, it's good enough to have that linear approximation. So for this, let's think about the Taylor series. So when we have this is a function of a scalar. This is a scalar input. If I take this Taylor series of this scalar function at omega naught, does anybody remember this? Let me actually ask, is Rudra Joshi here? Okay, so how do we write the Taylor series? Do you remember? No. Okay. So, so what we do is we take the function evaluated at the place where we're doing the Taylor series. Then we're going to look at the partial derivative of the function with respect to this parameter, w, evaluated at w naught. So that's going to be the slope, and then we have the deviation. So w is sort of like that's the variable of this new function. This is the reference point. This is how much we deviate from the reference point, and this is the steepness of the function, the slope of the function at that reference point. Okay, so are we done? No. We have to go further. So the next term would be what? What would we call the next term? Quadratic term. And then you have a cubic term. And you have a fourth power term and the fifth power term. You keep going all the way to infinity. Okay, but I don't have time to write all those infinite terms, so we're going to collect them all into just one term, one sort of notation, and we are going to call this big O, and then we're going to write the deviation W minus the reference W naught squared. Okay. So how many of you guys have seen this big O notation? Okay, great. A number of you have. So this is an important concept, at least to understand what it means. So there's an informal way of describing it and a more formal way. So the informal way, which is really all we need in this course, is that when you see a term like this, you say, well, that is really describing some more complicated thing. It's summarizing it in a simple way. And it's basically saying that thing, which in this case is like all the higher order terms in the Taylor series, is at most a constant times the argument, at least when that argument is close to 0. Now, if you want to get into the nitty-gritties, you can write it much more carefully. So if you say, I have a function g that is big O epsilon squared, it means there exists some specific constant c and some specific radius delta that tells us how close to 0 we are, such that this upper bound, the function less than or equal to c times epsilon squared, holds for all the epsilon in the radius between 0 and this delta. So this means that there always exists these two positive numbers such that this happens at least for some small neighborhood of epsilons. Okay, but basically for us, it just means there's all these terms there, but you know what? They're at most quadratic. So why do we use quadratic here and not cubic? Like, in this case, what's going to be bigger, the quadratic one or the cubic one? Right. Why is the quadratic one bigger than the cubic one?
Because everything on this W here is almost supposed to be.
That's right, because this is a small number, right? So if I have a small number, like a number less than 1, the higher the power I take it to, the smaller and smaller that gets. So cubic is going to be much smaller than quadratic. Quadratic is the bigger thing. Cubic would be smaller. So I'm saying this is at most quadratic. So there's a linear term here and a constant term, but the quadratic term subsumes all the higher order terms. Quadratic is the largest. It's larger than all that's cubic, quartic, and all that stuff. Okay, so that's this big O thing. And this is at least the picture that we're dealing with here. So, okay, last step, first order Taylor approximation. So this is the Taylor series. What about the Taylor approximation? What do you think it's going to be?
The first two terms?
First two terms alone. Basically, for the approximation, we just throw this out. So we get J at the reference plus the derivative at the reference times the deviation from the reference. And the picture probably tells the story pretty well. So this blue curve is your J as a function of W. This is your reference point, W naught. At that point, you can take the slope of the function. That's this. And now you can see that the linear approximation is basically, this red curve is like the best linear fit to that blue function at that point. If we move the points, like if we move this point over here, there'd be a different best fit. It'd be a different slope. But at this point, this is the best you can do. And you can see that there is some small neighborhood where they are actually pretty close. And that kind of gives you this idea. This is, for that small neighborhood, this is a pretty good approximation of the total thing. So notice we have an approximate equal to here, whereas we have an equal there. Okay, so this is the idea. We're out of time for today, but what we're going to do is we're going to generalize this to vectors and matrices next. And we'll come back and talk about this more on Wednesday. So I'll see you guys on Wednesday. And, yep, see you then.